Thanks everybody for coming, and hope so far the IoT conference has been hopefully very informative. I have a couple things to ask before we get started with the actual talk. Show of hands, because the audience varies in age. How many of you had a 2600 Atari machine? My 8-bit people are here. How about a Commodore 64, VIC-20? VIC-20 is more correct for 6502. Apple? So sitting across from me here is the person who actually put together the 6502 chip, was part of the design team, and actually, am I correct in saying you were the one that laid it out perfectly the first time? That's the lore?
That's lore. And actually, there are some people that would say he didn't lay out one thing on it, and that's probably true on that one. But basically, I chose all the transistor sizes, and I was a semiconductor engineer lead on that. I was the team leader to actually make it happen. Mm-hmm. So a guy named Chuck Peddle recruited me when we both worked at Motorola. So I had some successful designs there, and that's why he picked me out of the crowd.
Okay. And so just talking through a little bit of your earlier career then, so at that point, Chuck Peddle and you and the other members of the team put together the 6502. It went into the PET. It went into the VIC-20, correct?
Right.
And then at some point during that whole process, you had left to go work at the Western Design Center to create your own
Well,
company.
it was after Jack Trammell acquired MOS Technology, wanted to go into the game systems. I want general purpose microprocessors, so that's when I left to be a consultant, went to a consulting firm.
Okay.
But going back to the 6502, there was a 6501, and that was really what Chuck Peddle was promoting. 6501 was plug compatible with the 6800. Motorola came after us because we did use some of my original patents. So they said, you can't be plugging in your microprocessor, but I had already designed the 6502, which is about 12 transistors connected up in a different way that made it an internal clock generator. So actually, I promoted the idea of let's eliminate the two-phase clock system and make a single-phase clock system. And if we didn't do that, we would have been out of business completely because Motorola had us remove it. So they couldn't complain about the changes that I made, and that became the 6502.
Okay. And then that chip family has lived on in some form for all these years, right? You have a number of different systems based on this design. Let's talk a little bit about, so the chip design back then, I kind of said that you laid it out, the whole lore of you laying it out perfectly, but originally chip design was done basically by hand, right?
Right. What I did at Motorola, why Chuck would say everything I worked the first time. Well, it did work the first time, but whatever. There's semantics here.
Sure.
But the thing that I did, I had a bet with the operations vice president for MOS manufacturing at Motorola, and I think that's what a little folklore you've never heard.
Okay.
Made a bet. He says, this is at a dinner celebrating the release, the tape out they call it, a release of the 6800, and I said the PIA, which is the peripheral interface adapter, which I was the only engineer of, and I had one mass designer that I trained. He says, I said, I'll bet that my chip works the first time, and he says, oh, I'll take you up on that bet. And he says, so what do you want to make the bet? I said, dinner for two at a restaurant. And he says, okay, I know a restaurant here in Scottsdale. You can get a really expensive bottle of wine. I said, okay, well, my bet is the wharf at San Francisco with a really expensive bottle of wine. At that point, he goes, this guy's serious. And so it worked the first time. And so the reason why it worked the first time is something really basic. If you check it enough, you can really say it's going to work the first time. So what I did was I checked it 5 times the same chip with the same schematic, knowing the schematic was correct. And so my rule was that I would check it one more time after I didn't find any errors. So that would mean if I fell asleep in the middle of something, I might have missed one. So I was going with that into that bet knowing I was going to win. And he never paid off. He never paid off. So, yeah.
So let's talk a little bit about chip design then. So has anyone here ever done any kind of semiconductor design before? Like one or two or three? Okay. So for the rest of you, this hopefully is going to be a little bit of opening your eyes to some of the processes. So we have different types of chips, right? We've got your CPU, your computer processing chip, but even before then, you build chips, or at least they were originally built for very specific purposes, like a PIA. Talk a little bit about the ASIC process, which is the application-specific chip.
Okay, ASIC you're
Yeah,
talking
ASIC,
about.
yeah.
Okay, but let me go back to the PIA.
Yeah, sure.
The PIA, Intel never had anything of it. In fact, on the PIA, I got the first patent, before there were MaskWorks, I got the first patent on the layout of the PIA. I chose everywhere that the transistors would be laid out, and I convinced the patent office to give me a patent on it. That patent has been referenced to others. But the PIA, peripheral interface adapter, Intel never had one. And to this day, I don't think they have one. And what that means is that you could program each pin to be either an input or an output. And then to handshake 8 bits of data in and out, we had 2 handshake pins. So that's really not an application specific. It's a general purpose interface adapter where Intel would have 8 pins going out, 8 pins coming in. That's pretty specific. But having every pin programmable is really general purpose. And so that's what that did, and you controlled that with software. So now the ASIC is an application specific integrated circuit. So if you took, as an example, the microcontroller that's on an Arduino, that has some application-specific features to it. It's got some analog inputs. It has some digital outputs and inputs. And so, but if you look at it, it doesn't have an address bus or a data bus. And if it does, it's just got a little bit of the address bus and the data bus. So that's really the Arduino CPU that was first created, I think, by Atmel. That's more like an application-specific integrated circuit for the functionality of an Arduino. Now, if you look at that compared to the Raspberry Pi, then the Raspberry Pi has a CPU that runs at maybe 1 gigahertz or more. And so that's really general purpose. And you want to run whatever language you like writing, whether it's Java, JavaScript, C, or C++, or any of those languages. So that's really general purpose. Now, an application-specific integrated circuit actually usually uses a standard cell library. That means that there's standard NOR gates, NAND gates, inverters, but not transistors, which is interesting. Because you can't, with an ASIC, build a 6502 the way I built it, because of some charge sharing and other things. There's some things with an application-specific integrated circuit you just cannot do what a human mind can do, with some help from friends. So what I'm getting at there is an application-specific integrated circuit would be more like a garage door opener, but using a standard cell library. Now what's interesting about that is back in the 70s when I got started in this, the line width were like 8 microns. Now it's like 8 nanometers. So it's like 1,000,000 times smaller. And so when you get 1,000,000 times smaller following Moore's law of doubling the number of transistors every 2 years, think about how many times you doubled since 1971. A lot of times. That's like 47 years or whatever. So that's doubling a lot of time. So actually, you have a lot of transistors available to you. So you want to write in JavaScript. You want to have something that has 1 gigabyte of memory in it. You want to have a processor that may be a quad core running at 4 at 1 gigahertz. So that's 4 processors work on the same thing at 1 gigahertz. I mean, those are phenomenal numbers, but they're available for under $10. And so why not use them? They're available. So, but the application-specific integrated circuit approach is actually taking a hardware, you describe hardware with software. So everything's software now, even the hardware. And so, wow, okay, so then if you describe the hardware with software like VHDL is used in Europe, but our government defined it. So I don't use VHDL. I use Verilog because I could actually describe inverters and transistors in Verilog, but I couldn't do that in VHDL. The Europeans didn't get that. But we got it, and that's what we use in America, more or less use Verilog. So when you describe something that can be in an FPGA, which is the other thing,
The next one, yeah.
then you can use the same description for either an FPGA or a standard cell library called an ASIC. So then you make some trade-offs.
So the next type of chip would be the FPGA, Field Programmable Gate Array, right? So the difference between that and an ASIC, if I understand correctly, is the ASIC, you're basically burning an actual design onto a chip?
Correct.
Yes, the way that FPGA works, you have basically flash memory in there, inside it, and then you transfer that into what they call logic lookup tables. So to make a NOR gate, you might have, I don't know how many transistors make up a NOR gate, but that same logic unit can be a NOR gate, an AND gate, an inverter. It can be anything you put in the logic table. So it's a table lookup, which sounds so incredibly inefficient. And for a guy that likes to pick his transistor sizes and hook up his transistors the way he wants to, it's really a struggle. So I don't like writing RTL, but I do it. Register transfer level is what that means, RTL. So when you describe hardware with software, you give up a lot of the things that a semiconductor engineer like myself likes to do. And so I've had to adapt, and so I don't do chip design the way I did 30 years ago. Now I RTL.
And now, in reading about the process and what your company, the Western Design Center, does, you mentioned something called VASIC.
A VASIC is a marketing thing. It's like one of the speakers up here, I was thinking, boy, I wish I would have just clicked every time he used the buzzword. And it was like, oh my gosh, there's another one. Oh, there's another one.
I did it for you.
Oh, did you?
Just now, I think I did, yeah.
I thought,
Blame me.
yes, but VASIC is, think about it. An ASIC is an application-specific integrated circuit. So if you hardware describe something you want to put into that little square in the middle there, that's an FPGA built by Intel. Intel spent $16 billion a couple of years ago to acquire Altera, and that little chip is one of their most popular little chips. You can buy them for about $2 to under $10, but that holds a 6502 in it, or an 816, or both of them. And you go, oh, I could do that. So that also has the full memory map of the 6502 in it, has the PIA in it, has the VIA in it, has 4 ACIAs in it, an SPI, 2 SPI cores, and an I2C core. So if you want it, it's got it. But then what do you do with that? So that's where I'm saying a VASIC is a virtual, and this was used back in the 80s. They were calling these hardware description cores that were laid out or used standard cell libraries. They were calling them virtual cores or virtual components. Well, anybody that served in the Army, like I did, during during Vietnam, knew that VC stood for Viet Cong. So I never really liked VC at all, and I never used VC. But they're called IP, intellectual property cores. And some of them call them silicon intellectual property, so it's SIP. So all this jargon, all these interesting names people use, well, I came up with my own. The VASIC for virtual, but not that virtual component, but it's the same thing, but it's a virtual ASIC. But then, what I'm saying is everybody in the business, now maybe most of you don't know this, but the ASIC is a big deal. And so I wanted to go from a VASIC to an ASIC, and you'll probably have some questions about that, right?
So the 6502 and also Intel processors and a number of others were all built on what they call complex instruction sets.
Right.
Instruction sets to optimize the amount of work done per CPU cycle. And I know right now a lot of the chips for IoT they're all using ARM chips, and ARM is the reduced instruction set stuff. So, like, how would you compare the two, and what their benefits, pluses and minuses might be for application?
Okay, so Intel, in the form of their x86, that would be called a complex instruction set computer, and it's really an architecture. ARM stands for Advanced RISC Machine, which previously was called Acorn RISC Machine. So that's where the ARM came from. But ARM dropped the RISC thing. They don't want to talk about RISC because they added complex instructions in it. So they wouldn't even call their own processor today a RISC processor. So it's a game. It's a word game.
Naming game, yeah.
It's a naming game. But the first processor that was identified as a RISC processor was the 6502, because it didn't have the craziness that Intel put into their processors, or the craziness that Motorola put in theirs, because I already designed those processors, not Intel's, but Motorola's, and one before the 6800. So the 6501 was my third processor, and the 6502 was, if you want to call them numbers, fourth processor. So actually, the reason why the 6502 was so powerful was because of its reduced instruction set architecture. But what the reduced instruction set, RISC, stood for is not what it really meant. Did you know that to be called a reduced instruction set computer, which the 6502 was, could not be called that because it had to have an optimizing C compiler. So it had to have a C compiler. Wait a minute, that's not the processor, that's the software. But that, if you go back in the definition of RISC, you'll see that you have to have an optimizing C compiler because you have like 16 instructions, so you repeat these instructions to do things which my 6502 would do natively. So actually some of the things that you had to do with an optimizing C compiler was to reduce redundant code, so that's why you optimize.
Now, one of the things you are working on, and we'll talk about it a little later, is some hardware solutions that you're putting in meters.
Right.
And one of the concerns, I think, was power, right? So if you take the 65 CO2 or whatever the current version of it is, and look at its power needs, and look at then the difference between that and, let's say, a Raspberry Pi or even an Arduino, is it a significant power difference in terms of what they need to draw for doing work?
Another one of my patents is power management. So in my Mensch computer, which I sold 5 of them in 30 years, so it's not a really hot selling thing. But in there, I had power management. So each of the serial interfaces nowadays, this was designed before USB. So I had 4 UARTs in it, and I could power manage each of the UARTs. Turn them on, turn them off. So I actually would apply power to it. So what you do to reduce power is to turn off anything that doesn't need to be running. That's what they do in the cell phones. So actually my patent was used in every PC and every cell phone, but I never pursued them. So yes, so what that means is, think about it. Think about 4 COM ports, or 2 COM ports on each PC, and each one of those, if you multiply, it was like 100 milliamps. Doesn't sound like much, right? At 5 volts. And so you take that, that's a half a watt. Well, you take that times 1 billion, and you need a power plant. So that's where I was coming on. So when I shut off all of my UARTs, I had within the cable and the connector, I had the translator from the UART to RS-232. That's what they're doing nowadays. So that's what we were doing. So actually, if you think about sending 1 byte, or like what this LoRa, when you look at that, how many bytes are you sending? Is it 10, 100? That's all you need. You do not need a gigahertz ARM core running with JavaScript to send 8 bytes. So I'm just saying you don't need that, and if you want to work with this processor, it's still available.
And then also we were talking a little bit about these FPGAs and having maybe having that kind of hardware doing things like sensor readings as opposed to just a general purpose CPU. Is that also to keep A, the load off the CPU, and B, for power? Like, what would be the reason for doing it on the custom chip as opposed to on a CPU?
Actually, yes and no. What's going on right now in the world, I think you saw some of it in some of the slides. You have companies saying, how do I stay in business going forward? So if you sell a sensor, let's say you have a thermocouple company. You know, thermocouples, the electrical characteristics of a thermocouple says that it's hotter, it's got a different voltage than if it's colder. So if you were in the thermocouple business and some people said, I want to know what the temperature is, somebody that's doing logic, like a company that wants to be in the sensor business, they would convert that electrical characteristic with a ADC, an analog to digital converter. They would put on an interface onto it, maybe I2C, that's one, or SPI, sometimes a UART, a serial interface that has 2 or 3 or 4 wires on it, plus power and ground, and you would send them the actual temperature. So now if you were in the thermocouple business, you'd say, they don't want thermocouples anymore. They want to know what the temperature is. How do you get that information to the LoRa gateway, right? How do you do that? Well, you take that, and if the guy that said, I'm in the thermocouple business, I want to put an ADC on it, and I want to send 10 bytes of information or less to the LoRa gateway, then the sensor guy is going to get into that. So then he's going to deliver it to the gateway. So that's what you saw in some of the slides. So what you see is this radio is now attached to the thermocouple, and you send 10 bytes every 10 minutes, and then you can collect it all with Watson, and then you can say there's global warming. That's how that works. So then what I'm doing with the meter customer in Africa, that's why I asked the question, is it global? Well, I want to buy those gateways, but there's other lower cost ways of going. But anyhow, the point is that you take the electrical usage and you measure how much electricity was used, and then microchip makes a chip that puts out a pulse every time you use 100 watts or some number of watts. So that pulse is counted by a smart thing called a microprocessor. Any microprocessor can do this. I could say that every microprocessor ever designed by mankind could do an electric meter. Mine isn't. Come on. We're running at, 14 megahertz? That's like, really? Well, ARM runs at 1.4 gigahertz, right? And you go, yeah, but I can get it for, $20? Why not? But I'm looking at how you take the information from the sensor, collecting it with the processor, and you collect that with either a I2C, SPI, maybe a UART, and I have 4 UARTs on there for what? Wi-Fi, Bluetooth, GSM, which is really 2G, or LoRa, and I also have a development terminal on it. So I need these because that's what people do. So that's how this all fits together. So it means that how many radios do you want to hook up to it? Well, I need 3. Okay, the other guy only needs 2. So if you buy the one from Microchip, you can get it for $2, but why would you work with me? It's because you want to.
So I do want to ask a couple more things just around the whole ARM and RISC stuff. So apparently when Acorn first started coming into being, they visited you, right? To talk about their ideas.
Well, they wanted me to design it for them.
Okay.
But when they left Cambridge, you can watch a YouTube. Steve Ferber, I think it's F-U-R-B-E-R. He has a little video, and he'll say something like, so we got on an airplane from Cambridge, and we went to Mesa, Arizona, thinking we'd see this big factory or something else. And he shows up at this guy in a bungalow. That's what they call them in England, I guess, bungalow. It's a little ranch-style house. which I still am in. And so, been in since 1980. So, anyhow, so that, what he was thinking that I would want to design it for him because they had this idea. And actually, the guy that had the idea was, his name was Roger Wilson at the time. Now he goes by Sophie Wilson. So if you Google Sophie Wilson, he has a Wikipedia page, or she, I mean, has a Wikipedia page. And so they wanted to convince me to design what they wanted to do. And really what was behind the request is they were looking at using my 816 microprocessor. But then they realized, they found out about that time that Apple, Steve Wozniak came back to Apple, and they were doing an 816-bit computer, 816 computer, but they kept it under wraps. They call it the Apple IIX. And so this is going around, so this community. So then Steve and Roger wanted to leapfrog them with a 32-bit, and so they thought I would design a 32-bit and drop what I was doing with Apple, because they were the British Empire's equivalent to the Apple II. And so when I turned them down, I said, no, you want to do something that I don't want to do. So sorry that you take all this time and come over here, but thanks for visiting. And they were not happy. So they went back and said, well, if that guy can do it, we can do it in Cambridge. And so that's what they did.
And so now that you had mentioned that, you can't even call the ARM chip a true RISC chip anymore, there's another movement out there, right? So there's this RISC-V. And so describe a little bit about what RISC-V is.
Well, RISC-V is an open core. And so you know about open source software, right? Well, that's open source hardware. So now everything's open source. So build it the way you want it. What attracts me to the RISC-V over the ARM, first of all, open source, but the other thing that attracts me to RISC-V is the team behind it. So if you Google RISC-V, look at the team behind it. They're out of Berkeley, I think, about 10 of them or so. So they're really high-end architecture engineers, and they really know the thing. So if I were placing a bet on something, I would bet on a RISC-V. So if you want to get into hardware and software, or using hardware description, that's what that would be. If you wanted to do that and build your own thing from the metal up, which I think people might want to do sometime, I would use RISC-V. Now, ARM is owned by Japan, SoftBank. So they paid $32 billion for ARM. So when ARM first went public in 1998, I think it was, their market cap was $10 billion. So people often ask me, well, how do you feel about that? They took your business model, went public at $10 billion. I said, well, I turned down Prudential Beige in about 1985 because I didn't want to go public. I wanted to be me. So I was happy that someone took my business model, because look at what they've done to Intel.
So let's talk a little bit more around the Internet of Things, which is why everyone's here. Or I guess, as Don would call it, connected devices, wherever Don is. Let's say that we want to get started with an IoT solution. So we're iterating, we're prototyping, as everyone's talking about here. We're putting different components together. We find a particular end target solution that we want to roll out. What are some of the ways to go to the next step, to take that from being a bunch of wires hanging off of a board into actually manufacturing something?
Okay, so this chip here, can think of it as having 8,000 little wires. You get to pick how it's hooked up. Or if you work like we're doing, we hook it up to make it look like a 6502, look like 48 kbytes of RAM or memory, could be flash memory that's in here. All of these features are in here. Think of this as a prototype platform. That's what the FPGA is. But the other thing that's interesting is because of the cost of that device, you can actually start the market. That's what's big deal. You can manufacture the end product for, let's say, a year, pump out 1 million of them. By that time, you might have your market figured out. But if you don't sell 1 million of them, okay, well, it costs me, pick a number, $1,000 to get into business, and I can be selling it with unique characteristics as a VASIC. Then you say, hey, I figured it out. And I want to go from $5 per unit, which let's just say that's $5 per unit. But you're saying, well, I'm selling a new product, and I might even have a subscription fee around it. I might be making X amount per unit per month. That's why I asked some of that other question. And so what's the business model look like? I believe you can get subscriptions for this. Why? Because you can update this like you can your cell phone. What? I can update this CPU. I could change it from a 6502 to an 816 while it's running in your system. That's what you're doing with your cell phone, right? So this is hardware and software. So this means that now I can start the marketing effort, and proof of concept says, okay, I proved out the concept worked, but I actually sold 10,000 of them. So now, how do I make more money if I'm wanting to do this, let's say, not 1 million times, but 10 million times, like an electric meter? You go, oh, I can make that an ASIC, and I can get it for $1. Oh, I just saved, on 1 million units, I just saved $4 million, and it cost me about $500,000 to get it there. And that's a big number. You could probably do it for a couple $100,000. So that's what the VASIC to ASIC is about, and that means that you can roll your own. You can do whatever you want to do in that little chip, and it's cost effective. And then there's another thing. There's a serial number in each one of them. There's also an encryption key, so I can actually sell these boards with only the encryption key in it. I can sell the boards. You can go on my website and download a new CPU. I think that's awesome.
So as you're doing IoT work, and let's say there's people here are starting to work on different devices, what are some ways that they can come up to speed on enough information about electrical engineering and sensors and things like that? How does someone get a start if they're just getting toe in the water? It's a big open question.
That's a good open question.
Right? Burning out boards.
Well, when we were talking earlier, I said there might be 5 people in here that would want to go into these weeds, go down into the metal. So I don't know how many people would want to do that. If you learn how to work with a language, like Java maybe, then why would you work with this? I would say you don't want to work with this. I have more college-level engineering credits at accredited universities like Temple, Villanova, University of Arizona, and Arizona State University than Bill Gates, Steve Wozniak, Steve Jobs, Zuckerberg, and probably throw in a few more. I have more of them all combined, and I think they're wives. Anyhow, 220 college-level credits. That's like 30, no, that's like 70 classes at 3 credits. So I love physics. I love how to figure out where an ion diffuses into a background concentration in a semiconductor material. I love figuring out what the, what do they call that now? Depletion region in a diode is. All this stuff I love. I wouldn't recommend anybody here doing that. There's much better things to do with your time. So if you know how to write software, I would stay with software and find somebody that likes hardware.
You have a term that you use called, what is it, embedded intelligence?
Embedded intelligence. Yeah, now that seems so innocuous, right? Use those 2 words. Embedded. You ever hear of an embedded system? Is that a sprinkler system embedded in the yards of Arizona? No, it's an electronic system. But what do you, when you say embedded system, which has been used for 3 decades, I think, it's what Intel, I think, and Microsoft came up with. They're saying that, or maybe IBM too, but probably not IBM. They were saying, hey, if we called an embedded system, what we're really talking about, embedding a CPU board from a PC into an industrial controller somehow, or what they were doing in the first server farms, they were actually using a motherboard from a PC, and I think one of those companies were buying 1 million of those motherboards, just the motherboard, per month because of how many motherboards they had to replace. Maybe it wasn't per month, maybe it was per year, but they had to replace them because they have a life expectancy of 2 to 4 years, so they have to replace them all. That's an embedded system. So an embedded system is really, you could say more generally, an embedded microprocessor system. So your Arduino would have an embedded system. That's an embedded system. You embed it into something because you put a shield on it and you do something with something you want to do, right? That's an embedded system. So when I started using embedded intelligence at Stanford, when I was there visiting them with the advisors, I was an advisor at Notre Dame for 22 years. I'm no longer an advisor at Notre Dame College of Engineering, and specifically the Computer Science and Engineering Department. I was the chair of the review committee for I don't know how many years, maybe 15. So when I used this term at a meeting at Stanford in a garden motel thing on a brainstorming session, I thought everybody knew what embedded intelligence was. And Intel inside, doesn't that tell you the same thing? But Intel stands for Integrated Electronics, not Intelligence. And if you know about their first processors, they weren't very intelligent. But then again, Intel inside is a multi-billion-dollar ad campaign that's been going on for maybe 20 years, I don't know. The original budget for that was $500 million. So now, when you think about embedded intelligence, I'm saying that's so obvious. It's like when I brought it up at this meeting, everybody's looking at each other and saying, what's he saying? What? Embedded intelligence. I don't get it. Embedded systems. Oh, I get that. I don't get embedded intelligence. And then I'm thinking, how's that possible? So when I put together some slides that you can find on my Mensch Foundation website, themenschfoundationwebsite.org, what you'll find is some slides that someone helped me with, Dave Kramer, actually my marketing guy, in 2011. That's a year later. And I said, just look up something, because I had an hour to present, put together some slides so I wouldn't wander all over the map. He couldn't find anything that had those two words connected together in 2011. And then I'm thinking, no, did you misspell something? So then we did that. I gave this talk to the kids and their grandparents at the Spark Shop. It's actually the Mensch Spark Shop in the Durango Science Center. I said, 2 years later, no, he must have missed it. He didn't do a good search. And then I went to search it, and the only thing I could find, this was about 2013, the only thing I could find was what you would have heard about right now with LoRa. It was Ricoh working with IBM to put in, I think, an environmental system into the big buildings in Tokyo. I saw it used properly, embedded intelligence in that building. And you go, oh, isn't that what we're doing today? How about embedding intelligence into your automobile? And then you start using words like, no, I don't like embedded intelligence. Okay, you don't like it. I think it's a good word, but nobody wants to use it. I like artificial intelligence. So then I say, okay, so artificial intelligence is to embedded intelligence like a square is to a rectangle, because artificial intelligence was defined in 1956 with about 5 professors at Dartmouth College. And so you go, well, does that still apply today? So you want to put artificial intelligence in our cars, right? The definition was man-made intelligence. That's what artificial intelligence. But more importantly, the definition was artificial intelligence if you had a computer like the Turing prize is if you could, it's like Watson versus me, okay? What's the temperature out there? Watson would come back with, it's 53 degrees out there. Me, I'm going, could somebody run out there and get, so if Watson answered that it's 53 degrees and I'm fumbling around for, well, I need somebody to help me get that answer, then they'd say, oh, Watson is not a human because he's so much smarter than a human. But back then in 56, they were thinking that a human was pretty smart. And I'm thinking, wait a minute. So actually artificial intelligence in an automobile, if it replicated the human, I don't think you'd buy the car. Because the car doesn't work right. So in other words, artificial intelligence, I believe, is a dead term, but it's going to be used because it has some emotional content that'll have us continue to use it for a long, long time. but it's all about embedded intelligence.
So the concept of the edge, the IoT device having intelligence is, I think I saw the Hortonworks talk was talking about having some machine learning, lightweight machine learning libraries at the actual edge.
Well, you build the intelligence in that it needs to function the way you want it. That's what the key thing. That's why I'm saying at 1.4, I saw the latest Raspberry Pi, a quad core running at 1.4 gigahertz with a gigabyte of memory. Okay, that could be really smart, but I'd rather do it with less transistors, that's all. And so you see, the embedded intelligence idea says, why don't you match the intelligence up to the thing that you're doing? That's the whole key here. So my 8 and 16-bit processors is all you need for a lot of things. I'm not saying a quad core run at 1.4 gigahertz isn't really cool. I'm just saying it's a bigger hammer for a little nail. And so that's why I'm saying, well, maybe we'll find some applications with what I'm promoting as an 8-bit processor. Now, the competitor would be an 8051 core, maybe the PIC core, which is pretty awful processor actually. The Atmel core, that's pretty good. So there's all these processors can create this embedded intelligence for the application.
Also, I wanted to make sure we had time for questions. So, does anyone here have a question for Bill? I can come down with Mike.
So you mentioned the edge a lot. Where is the edge? Is it the gateway, the sensor? Could it be either?
Okay, the way I use edge, which I think is the way most people use edge is where things happen. What does that mean? It's what you sense. So it's where the sensor is located. It's where the actuator is. So an example would be you would have an edge processor. You'd have an edge processor with your thermostat. We heard about thermostat, I think, earlier today. So it would be sensing the temperature in the room and then turning on the heater or the cooler, and that's what would be going on in a refrigerator. So you'd say, well, it's too warm for my food, so turn it back on. So that's the edge. So you have trillions of things in the edge. You have any idea why I'd rather work in the edge? There's a lot more processors in the edge. So if I get a small fraction of 1% of that trillion, I got a big number. And so that's the edge. The gateway, Intel, I think, and others call the fog. The fog is where you have more processing. So the fog is where you would maybe have, as you're driving down a freeway, the fog might be along the freeways in California or in Toronto or someplace like that where there are a lot of cars. So a lot of cars means there's a lot of possibilities for something to go wrong. And you can easily see that the fog means that you're spreading it out to like the fog on, thank you, the fog that we had the other day that we don't have in Arizona. But the fog is really closer to the edge then, right? Or touches the edge. You could think of it that way. And that's the way I look at it. So then the cloud, you know about the cloud. So then you have the cloud, you got the fog, you got the edge. And I was using the edge just because I knew that the edge is where things are happening. I want to be where things are happening.
For battery-powered applications, the processors you're working on that run at lower clock speeds, is that one of the reasons you're able to get the low power because of the lower clock speed?
Yes, but there's another reason. Is just think about it. You're using an ARM core with a 32-bit data bus, a 32-bit address bus, and you're moving bytes of code around. Now, give me a break. Why would I use a 32-bit processor with a 32-bit address bus and a gigabyte of memory to tell me what the temperature is? You just, because it's available, because I can get it for $2. And you go, yeah, but do you think don't you want to be more creative than that? So what I'm saying is lower power is also using less transistors, less nodes to charge and discharge. And then you have the other thing is, hopefully you're doing something smart. What does that mean? You're embedding intelligence in your product, right? That means that you say, hey, I'm not using you, so I'm not going to send you any information. Okay, well, when I want you to do something, I'll send you a byte, and that will give you a command. And then I'll send you a byte. Now you say, I would send you just 1 bit if I could, but it's really hard to go from 8 bits to 1 bit and make that make sense. So what are you going to do with that 1 bit of information that is packed into 1 byte? I'm going to turn on the light. I'm going to turn off the light. That doesn't even take 8 bits. So when you do that with a gigahertz processor with a gigabyte of memory, you got to go, well, maybe it's a little more than I need, but that's what my boss said to use. So I'm just saying that when you ask me about power, is if you shut off the things that are going up and down, charging and discharging a node, by definition, you're reducing the power. So you, by design, can design in how much power you want, and you don't have to use it.
Thank you, Bill, for speaking with us today.
Yeah, so thanks for inviting me into this software world.
We sometimes let hardware people in.
Yeah, well, thanks.
All right, thank you.